Hey, welcome. You know, our planet has this absolutely epic story to tell, a history that goes back billions of years. But here's the thing, it's not written in any book you can find, it's written in stone. And today, we're going to figure out how to crack that code.
So, think about it like this. How in the world do you read a diary that's 4.5 billion years old? I mean, where would you even start? The pages are literally mountains, the ink is made of minerals. It seems impossible, right? Well, it turns out scientists have found the key.
And that key, well, it's hidden inside the planet's own secret diary. It's rocks. Every single rock, from a tiny pebble you'd find on a beach to the very peak of Mount Everest, holds a piece of the story.
Now, this is where it gets really cool. We're not just looking for fossils or counting layers here. We're looking for something much more fundamental. See, inside every rock is a kind of hidden clock, an atomic timer that started ticking the very instant that rock came into being.
So the big question is, how do we read this clock? And this brings us to one of the most powerful tools in all of geology, nature's atomic clock. And that's not just a metaphor, it's a real, measurable process that's happening inside the atoms themselves. The official name for it is radioactive dating, and the idea behind it is actually beautiful in its simplicity. You've got certain atoms, like uranium, that are unstable. We call them parent atoms. And over vast amounts of time, they predictably break down, or decay, into new, stable daughter atoms. This visual shows it perfectly. So, those pink circles, they represent the unstable uranium atoms, the parents. And as time goes by, they just steadily transform into the stable blue lead atoms, the daughters. The magic here is that the rate this happens at is perfectly constant. It's like the most reliable clock in the entire universe.
Okay, so how do scientists actually use this? Well, it's basically a three-step process. First, they take a rock sample and they count up the parent and daughter atoms. Then, they look at the ratio between them. So if a rock has a ton of parent atoms and just a few daughter atoms, it's young, right? Its clock has just started. But if it has way more daughters, well, that's the telltale sign that its clock has been ticking for a long, long time.
All right, let's put this incredible technique to the test. For our first case file, we're going to try to solve the mystery of the moon's age. Just how old is our closest neighbor in space?
So, the first real clues didn't come from Earth at all. They came from space. The Apollo astronauts, they actually collected rocks from the moon and brought pieces of its diary all the way back home for us to read. And these things, they weren't just rocks, they were genuine time capsules. So when scientists analyzed these tiny little crystals inside those moon rocks, they found something amazing. The ratio of parent uranium atoms to daughter lead atoms was almost perfectly 50-50. And what that means is that exactly half of the original parents had decayed. This moment in time is called a half-life, and for uranium-238, one half-life is a really long time.
How long? We're talking 4.53 billion years. Just like that, using this atomic clock, we figured out that the moon formed right after the Earth itself. It was a huge piece of evidence for how our solar system came to be. A major planetary mystery solved. Okay, for our next case, let's fast forward a few billion years. We're going to investigate one of the most famous crimes in prehistory. What killed the dinosaurs? And more importantly, what was the murder weapon? Well, we found a prime suspect. It's a massive impact crater, over 100 miles wide, called Chicxulub, and it's buried deep under the Gulf of Mexico. For a long time, this was the #1 theory. But geologists, they needed a smoking gun.
And this is just wild. The crime actually created its own evidence. The sheer energy from the impact instantly melted and vaporized the rock at ground zero. And as all that superheated material cooled down, it formed new minerals, resetting their atomic clocks to tick from that exact same moment, the moment of impact.
But here's the million-dollar question, right? It's one thing to find a giant crater. It's a whole other thing to prove that it caused a global extinction. The timing had to be perfect. So could radioactive dating actually link these two massive events together?
And the answer was a resounding yes. When scientists dated the melted rock from inside the Chicxulub crater, the atomic clock read 65.5 million years ago. It was a direct, undeniable match for the date of the mass extinction event that we see in the fossil record.
As one scientist famously put it, the date from the crater was the smoking gun. It was the final, critical piece of evidence needed to prove, beyond a reasonable doubt, that an asteroid was the dinosaur killer. Case closed.
So for our last section, we're going to zoom way out. We're going from single, catastrophic events to a process that has literally shaped our entire world. We're about to see how reading these atomic clocks reveals the actual blueprint for how continents are built.
Because, you see, when you stop dating just one rock, and you start dating thousands of them all across a continent, you stop seeing individual ages, and you start seeing a grand planetary scale pattern. It's kind of like putting together a giant puzzle, piece by piece.
And this map just reveals a stunning pattern. This shows the age of the bedrock across North America. And you can see it, right? The oldest rocks, they're all clustered there in the center. That's the ancient core of the continent. But as you move out towards the coast, the rocks get younger and younger. Why? What is going on here?
Well, the answer comes down to a really basic difference between the two types of crust that make up our planet's surface. You've got oceanic crust, and it's just denser than continental crust. So when they collide, the heavier oceanic crust always loses. It sinks back down into the Earth, while the lighter continental crust just kind of floats on top. And here it is. This is the big reveal. Let's look at the Pacific Northwest. You've got this dense oceanic plate called the John de Fuca plate, and it's sliding, or subducting, underneath the lighter North American plate. And as it sinks, it literally scrapes off chunks of land from the ocean floor and just plasters them onto the edge of the continent. It's like adding new pieces to a collage. The age map isn't random at all. It's a photograph of a continent in the middle of growing.
And what all this means is that this process, plate tectonics, is the engine that is actively shaping our world. I mean, this isn't ancient history. This is the force that built the Cascade Mountains. It's the reason that region has active volcanoes and earthquakes today. We are literally watching a planet being built in real time.
You know, from a single atom decaying inside a crystal to the collision of entire continents, the story of our planet is one of constant, incredible change. The atomic clocks hidden in the rocks have let us read the past, and they show us that the very same forces that built our world are still hard at work today. And it just makes you wonder, right? What new chapters are being written in stone right now?